So for chapter 9.15, the question is, a high-speed flywheel in a motor is spinning at 500 RPM. When a power failure suddenly occurs, the flywheel has a mass 40 kilograms and diameter 75 centimeters. The power is off for 30 seconds, and during this time the flywheel slows due to friction in its axle bearings. During the time the power is off, the flywheel makes 200 complete revolutions. So for A, at what time is the flywheel spinning, and when the power comes back on. So for this equation, we're going to use a few different rotational motion equations. So first we have these three equations right here that we're going to be using. We have our different, what each I guess Greek letter means. So we have our final velocity for omega. Omega is 0 is initial velocity, t is time, alpha is angular acceleration, and theta is angular displacement. So we're also going to be using this equation right here. So we have our angular displacement right here is equal to our final velocity plus our initial velocity over 2 times t. So for A, to get our answer here, we take the angular displacement, which is equal to 200 revolutions, so essentially, in order to find this, we set the equation equal to our final velocity, omega here, and so we set it equal to our final velocity, and since our displacement is 200 revolutions, we plug in the numbers for theta minus initial theta over t minus our initial velocity. So we have 2 times 200 over 0.5 minus 500, and that gives us 300 RPMs. So that's how fast the flywheel will be spinning. So then for B, the question is, how long after the beginning of the power failure would it have taken the flywheel to stop if the power had not come back on, and how many revolutions would the wheel have been made during this time? So B, we use another equation for angular acceleration. So we use alpha equals our final velocity minus initial velocity over time again, which is 300 minus 500 over 30 seconds, which gives us minus 400 revolutions per minute squared. So we take our final, velocity, and set equal to our initial velocity plus alpha times time. Our final velocity is 0. We can see that our final velocity here is 0, and so we can set that equal to our initial, and etc. And then we solve for t, and when we solve for t, we plug in the numbers, which gives us 1.25 minutes or 75 seconds. So that's how long it will take it to stop, and how many revolutions would it take. So we take the angular displacement and set it equal to, we just basically take the same equation that we had before up here, right here, and we plug in the numbers again. So we plug in at 75 seconds, and plug in the rest of the numbers, 300 plus 500 over 2, 400 times 1.25, and this equals 500 revolutions.